Yo, hello.
Hey.
Welcome back to Monadic Design Patterns for the web. And I'm not going to give you any preambles. I'm going to start some code right now. So I am now starting up a Jetty web container. And we're going to see some code in action. And so now I'm going to get a browser up, pointed to HTTP localhost. There we go. Oh wow, there's a little project that's up and running based on the Lift web framework. And I'm going to log in as someone named John Conway, and that will become important and interesting in just a few minutes. All right, and now I'm going to launch a little calculator. Now you've seen calculators before a bazillion times, and this one probably doesn't even look very fancy. Let's see. There's 13. Now what's this funny thing with all the parens here? And let me add 5 to that and say what that's equal to. Wow, that's really weird stuff. Actually, what's going on behind this calculator is that we are using Conway numerals, Conway Games, to do all the arithmetic. And all of this is running. It's running inside Scala. You can see if we bring the Emacs window back up, that as we were clicking buttons here, let me see if I can make this thing, as we're clicking buttons here, so I can clear that out and clear it out again. Oh well, we didn't quite get the events, but anyway, the thing is running as we speak. So let's get into what's actually happening behind the scenes and why that's relevant to monads and monadic design patterns for the web. Okay, so let me launch into the slide view, slideshow mode. So I'm going to talk about some things that are probably near and dear to a lot of programmers' hearts. One is the notion of inheritance and reuse. Probably a lot of people are already on the bandwagon that inheritance actually gets in the way of reuse. But I want to talk about that and sort of why, and use that as a launching pad into a way to think about monads, and in particular to think about it as an API, and then how best to use that API, and then give some data structures that give this idea. And do I stare right into that guy there?
If you want.
Okay. And it turns out that like the minimal structure that can give some of this is turns out to be Conway Games. I was just looking for a simple data structure that had 2 containers as components of the data structure.
Okay.
And it just turned out that Conway Games fit the bill perfectly. And the funny thing was, I happened to whoa, that's not fair. It really wants to have the little bar there. Okay, it turns out that I was teaching Conway Games to some 4th graders at the same time, so that was very nice. So what I'll do is I'll generalize those and then give them monadic structure, and then talk a little bit about reuse, again, kind of tie it all up. And I really need to acknowledge James Irie, he's a influential voice in the Scala community. I recently posted this material as a blog post, and he tweeted that Scala is a big tent while everybody else is scaling the web and DSLing LGM, that's me, is abstracting Conway Games over arbitrary monads. Now, in some ways, that could be a poke in the ribs, because I still haven't finished my my Monadic Design Patterns for the Web book. But what I want to do is to show how this material actually fits perfectly in line with that. And kind of connect the dots for people, because it looks like there's just a lot of opportunity across communities to begin to talk if we can connect the dots. So first question, what does reuse really mean? And the proposal is really very straightforward. The idea is that whenever we can substitute a piece of code in some context, right, for some other code that does the same thing, then that's really a form of reuse. That's actually when we're getting some reuse. I had some code in this place. I'm going to swap it out and use some other code. That's really, substitutability is a very good characterization of reuse. Now the problem is that what's this does the same thing idea? How do we characterize that? So in many cases, types are a fairly decent approximation, right? So if the thing, demands something of its environment and emits this other thing of its environment, we can kind of substitute in, if it does the same thing, So a function from int to int, well, I could swap one for the other, sort of, kind of. That's not really enough information to be safe, right? Because the identity function will go from int to int, right? And calculating the nth prime will also go from int to int. And so swapping those two isn't going to give you exactly the same behavior. So usually what we do is we need some additional context information to sort of characterize what we mean by does the same thing. So let's give a concrete example. So we could say that sets are functions from the universe from which we build all sets to Boolean. Okay, so my set, if something is in the set, true. If it's not in the set, false. Right? So I could look at every set as though it were a function. So if I were writing Scala code, we'd want to say something like this: set A is the same as A to Boolean. It turns out, though, that a statement like this presumes a great deal about what sets are and what functions are and what universes are. A lot. In fact, it sort of presumes like the whole like the last 100 years of computing and mathematics, right? Which is not the best presumptions. There's a lot of fine-grained and interesting information kind of in the details there. So if the devil is in the details, well, there's a lot of devil there. Now, another way to go about this would be to say that in the world of higher order functions, where I can kind of pass functions around the return functions, it's easy to reify our assumptions. So I can make a trait, sets can be functions, which is parametric in a source and a target type. And it has one method inside it, and that method is as function, and it takes a set and it returns a function from S to the target type. Now notice that my target type isn't necessarily bool. It could be bool, so I could say sets can be total functions. So that would extend this trait, and it would take the type S, and Boolean is the target. Okay, so now we've recovered this idea of sets as functions. But notice how general this is. We can also say sets can be fuzzy, right? So now we have we extend sets can be functions with S and double. Really what we want is the unit interval here, but I didn't have sort of a ready-made type for that, and I just wanted to get the idea across. But really, fuzzy sets are exactly, we have fuzzy membership. It's not 0 or 1. It's somewhere in between 0 and 1. And you can also have partial functions, right? So it's either in, out, or I don't know, right? So this characterization here, this parametric characterization, which will take a set and give you back a notion of a function, is much more general. And it allows us to very carefully and concretely, with compiler support, no less, reify our assumptions about how we turn sets into functions. Okay, so that's a different way of doing things in terms of reuse. We could say, well, sets inherit from the type function from A to Boolean, but this is more flexible, right? And I'll come back to that. But let me summarize what I'm saying here. So ISA relationships are more often than not meaningful in some context, all right? And ISA is a way we think about substitutability, so tie it into this idea of substitution. If orange and apple are fruits, then in a fruit basket I could have an orange or an apple, right? But more often this ISA relationship is meaningful in a context. There's some context in which we think about that they are that thing. And outside of that context, we don't make that identification. right? In the higher order approach, the crucial point is that we can reify the context. We make a thing that represents the context. So here the trait is the thing that represents the context. Okay? And so we have a representative for our assumptions. And that's actually more object-oriented than object orientation generally. Right? Because we actually now have a thing which represents the context. And then, but inheritance sublimates the context of an is-a relationship, and it eliminates the representative of those assumptions. So that's the difficulty. Now, the reason that's interesting is when we think about monads, the crucial point is that monads are a view on structure. They are not the structure. A list is not a monad. A set is not a monad, right? That may sound blasphemous to some people, but that's the case. The monad is actually the view onto list or set or tree or whatever your data structure is. Okay, so that has significance in terms of how we structure our code. So let me give a quick recap here. So a monad is going to be a higher kinded type. So what do I mean by that? Well, it's a type constructor that takes a type which is also a type constructor. So that's what I have in the past called the shape. Okay? And then you have a way of putting things inside the shape, wrapping them up. So you take for example, an A, and then you put it inside the M shape. And before I talked about role, which was a different kind of presentation than this one. This is more Haskell-y in style. This is also link-like. Okay, so this is the bind idea, and so, sometimes I call it the jelly roll instead of the roll. So the idea is I have a function which goes from A's to B's that are inside the shape, and I have an A already inside the shape. So somehow I have to get the A into this function to get the MB, and that's what bind does. So it's a kind of jelly roll. And it turns out that there are simple examples of this. So, but the crucial point is that the list monad is not list. It's monad of list. Okay, so that's different. And then we can give our usual definitions. So the unit for the list monad is going to take an S and put it inside a list. Oh, that should have been an S, not an E. Sorry about that. I think I may. Yeah, no, that's correct. And then the bind is essentially going to do a fold over the list in such a way that we accumulate each of the lists that we create by calling this function on each element. So we're just concatenating along into the accumulator, and that's what we'll return is the flattened structure. Okay, so now very simple code, but the simplicity is also hiding something because we're up a level of abstraction. This thing is not a list, it's a view onto the list. Now, the crucial point is that when we look at containers like list, set, tree, that all of those operations all have the same shape. And so it all feels very canonical. It doesn't feel like there's any wiggle room, any choice about how you might effect these definitions if you have the monad laws lying around. Okay, but what we'd like to do is to show situations where we do have wiggle room. Okay, so we need a container big enough to hold some wiggle room for us. Okay, and the simplest container is going to be one which has components which are also containers. So, can I?
Yes, you can.
Awesome.
Here you go.
Sweet. Very good.
It's okay, man.
Oh, all right.
Rock and roll.
Okay. So, what I'm really saying is, if a monad is a shape, and we have this idea of putting things into the shape, and which includes when I have something inside a shape, putting it into the shape again, right, and then being able to canonically flatten those. What we now need is a container that has at least two components which are also containers, right? And then the idea is that when I interpret this container as a monad, I'm going to be able to say, well, when I put things into the container, I could put it here or I could put it there, sort of a Dr. Seuss-like thing. You know, you could have it here or there, right? That's where you can put your green eggs and ham.
Cool.
All right, so let's take a look at that in more detail. It turns out that a structure that has exactly this shape and minimally this shape is something known as Conway Games. So this fellow here is John Horton Conway. He's one of the most amazing mathematicians of the last century and this century. He's still alive. People may not know this, but the idea of quantity, you know, we think we understand numbers, but it's actually our relationship to numbers historically is haphazard. We sort of wandered all over the map in terms of how we think about numbers, right? The concept of zero as a represented entity came very late in the development of our relationship to quantity. And Cantor, for example, he thought of all these crazy infinities, and people thought he was crazy until he realized there was some sense into it. But that's also a notion of quantity and order. Likewise, Robinson was able to show that the infinitesimals that we do in calculus, right? So when we write, you know, something like, you know, integral x dx, you know, engineers are happy to think of that thing as a multiplication. Drives mathematicians crazy. But Robinson was able to show that there's a world in which that makes sense as a kind of multiplication, and that these things really do have a right to be thought of as numbers. So Conway's contribution of many that he made was to provide an organizing data structure which encompassed all of those different ideas into one simple data structure that has this characterization that we've talked about in the preamble here. And it turns out that representation also has an interpretation as games. He calls them partisan games. And those things are not just mathematical oddities. For example, one of Conway's collaborators, Berlekamp, was able to show that you could apply these ideas to Go and found surprising strategies that won in situations that masters were surprised, Go masters were surprised by. So the idea of chilling, which you can read about in the Mathematical Go book, came out of that analysis. So the idea of games are very, very simple. A game captures the options of the player and the options of the opponent. Okay? So player has some moves, opponent has some moves. When a player makes a move, it gets to a new game, which is just a collection of options for the player and options for the opponent. So it's a recursive concept, and we can actually capture that in code. Okay? So we can say abstractly, a Conway game has two components: a left, which is a set of Conway games. So these are the options for player, and a right, which is again a set of Conway games, and these are options for opponent. And so in terms of the abstract shape we were looking for, this is exactly the droids we were looking for. Okay. And we can now we can actually make that concrete. So you might think that this is just horribly recursive and won't bottom out, but actually it does bottom out because we know that there's at least one set that we can make, and that's the empty set. It doesn't have any Conway games in it, on both the left and the right, and that's exactly what the empty game is, right? So it has an empty left component and an empty right component. And that's a very concrete type that we can instantiate and look at the prompt. And in fact, that's what we were doing when I was running the little code at the very beginning.
Excellent.
Likewise, we can make concrete classes that extend our abstract trait, where we now have a value, which is a set of Conway games, and a value, which is a set of Conway games. So it's no longer some abstract method, but in fact, a real value that we have in our hands that we can manipulate. So let's look at some games. Well, Conway calls the empty game 0. And then once I have a game, now I can make a set of them, which is the set that just contains that one. And we call that 1. So we have a game in which the left component contains the set containing the empty game, and the right component is empty. Once I have 1, I can make 2, and so on and so on and so on. Likewise, I can do the negative integers as well. Okay? So the negative integers have an empty left component, and I put 0 in the right-hand side, and so on. Now, what if I wanted to do, for example, the rationals? Well, Conway shows that you can get the dyadic rationals, and in general, the idea is that the game as a number can be thought of as this set points upward towards the number you're interested in, and this set points downward towards the number you're interested in. In this case, we have 1 pointing up to 0, so it's in between the two. It's 1/2. I might have got those mixed around, but it's not so important for our discussion. Okay, so now here's a crucial idea. We're now going to look at arithmetic on these structures and show that we can actually do arithmetic on these structures and that it behaves as ordinary arithmetic. Okay. Now, the sweet thing is that this is very Conway calls them sort of one-line definitions, right? So it's very recursive. So to do the minus of a Conway game, remember it has a left and a right component. So either if it's empty, it's just empty. So the negative of 0 is 0. The negative of a concrete game, we flip left for right, and then over all the ones that are in right, we negate them again. And all the ones in left, we negate them again. Okay? So that's negation, taking the negative. We also have definitions for add and multiply. And we can take a look at code. I can also point you to the repository, the GitHub repo, where that resides. But let's just take a look here. So you guys can see that this is real code. And so here's the Conway calculator code. And here is addition. What we do is we add to all of the left components of G1. So if I'm adding G1 to G2, to all of the left components of G1, I add G2. And to all of the left components of G2, I add G1. And the combination of those two gives me the left component of the added game. Okay. And likewise, for the right, I add all the right components of G1 to G2, and I add all the right components of G2 to G1. And when I take the combination of those two sets, so the union of those two sets, then I get the right component of the sum game. And there's a more complicated definition for multiplication, which I'm not going to go into, but you can look at it in the repo, or you can look it up online. Just the main point here is to know that the definitions are elementary. I want to go here, slideshow. I want to make a quick point, and this is related back to James Irie's comment, actually. Conway has his own notation for these things. So he uses a set-like notation where we have squirrely braces and a line in the middle. So you have the left stuff on the left of the line and the right stuff on the right of the line. So players' options are between this squirrely brace and the bar, and opponents' options are between the bar and the next squirrely brace. So that's 0. 1 would just be put 0 on the left side, which looks like this because by the definition of 0, and 2, and so on. More generally, he says a game is ranged over in the left by G upper left and ranged over in the right by G upper right. So our definition of minus is now expressed this way. Now, compare the notation to the code you saw before. The code before was very, very succinct, being a functional language, right? If you tried to do that in Java, it would be tedious in the extreme. But here, this is far more compact. And I want to make a point that kind of links to cultures. Mathematicians by their nature, are DSL designers. That's what they do. They design little notation systems, whether it's boxes and arrows and diagram chasing for category theory, or Conway with his game notations. They design DSLs. That's what they do, and utilizing this fact to understand how we take this kind of the elegance and compactness and get some power out of it is an important thing, because it turns out that having a good syntactic representation unburdens the mind. Right? Okay, now Conway games are pure. So if you looked at our definition, they contain nothing else other than Conway games. Either it's the empty game, or if it has other things in it, it has Conway games. Nothing else. And that's just like ordinary set theory. Ordinary sets only contain either other sets or nothing. Okay? But we talk about set-like data structures, right? And the idea of sort of going from a container which has no duplicates and is order insensitive, that's really what we're talking about. We can do the same thing for Conway games. Essentially, whenever we poke a hole in set, because Conway is built on top of set, we can poke a hole in Conway. Okay? Now, the crucial point there, though, is that we have to be a little bit careful when we extend this to our arithmetic operations. And the reason we have to do this is monads need a type constructor. They need to be parametric in something. They're a higher order creature, right? If we go back, right, all the way to the beginning, there. Our type constructor has to have a hole in it, right? So if we want to make a monad that has these two components in it, we've got to poke a hole in it. Right now, Conway games, there's our trait, no hole. I got to poke a hole in it. And the analogy of poking holes in sets holds exactly the same. We poke a hole in the Conway game in the same way that we just poked a hole in set. Okay? And this general idea of hole poking actually works quite well. So here, what we do is we say that the generalized Conway game, now with a hole in it, has its components, and either it's going to be an A or a generalized Conway game. So either I've actually got something, an atom in my hand, or it's one of these, recursive things. It's another container inside. And likewise for the right-hand side component. And the rest of the machinery remains undisturbed. Okay, so that's beautiful. But when we negate, add, or multiply these things, if you remember the definitions, so here we go. If what's inside here can be either a game or an A, I'm going to have to negate not only games, but A's. And when I add things, I'm going to have to not only add games, but I'm going to have to add games to A's and A's to A's. Okay, so how can we do that? What do we do? Well, the crucial point in that is that we defer this. We say, I don't know. I'm going to invent some syntax which just records the fact that I have to do it. And that is also a monad. That's what monads are all about, is deferring and reifying computation. So we just make up some syntax. We just capture the syntax. I promise you I will add these two later. Right? And then we let some other calculator define for us what that addition means based upon further information it has about the type. So this won't work in general. It will work in places where the types have enough information to carry that. Right? Okay, or we push it all into the syntactic structure, the reified structure that we did before, which was, if you remember the very first C9 talk I gave, I showed how you can make that work as well. Okay, now, but here's the trick, right? The trick is we now have two components. we can put, if we do a unit for this thing, we can put our A into the left side, right? Because there it is. Or we can put it into the right side. Now we have two views. If I were going to say this is a monad, then I would be forced to commit early to one side or the other. And that's not good for code reuse, right? I'd have to go make another one of these for the other side. Instead, what I say is there's a view above this. What kind of view? Well, the view looks like that. There's the view, and I can make an instantiation of the view like this. Okay? But here, instead of being the list monad, it would be the game monad, and it would be monad of Conway game, generalized Conway game. Okay, so again, you can see this code in action. So we have the generalized Conway monad, and here it is. So there's the generalized Conway game, and the formal notions, I don't know if you can see that, but you have the generalized Conway game, there's a concrete version of it, and you have the formal notion of negation with a left and right. We have formal sums, and then we have the monadic scope. Let's see, where's the, oh, I know what I need to do. I'm in the wrong directory, GenConM. Right. And here is in fact the unit. There's a GenCon left, which puts the unit into the left, puts the S into the left, and likewise there's a GenCon right, which puts the S into the right-hand side. Now the interesting point is that if you do the calculations carefully, you'll see that the bind for left and right have to be the same. Right? And there's a place where we do want to pull some code upward. Right? So we have a pre-monad class which has the generalized bind, which is common to both. Right? Now, if we were really religious about all this, we'd reify the context of our assumptions for this as well. Right? So that's that code is running. Now, the crucial point about this code is that the dog doesn't bark. Okay? Which means that the calculator for this is exactly the same. It remains unchanged under the assumptions of that we have a notion of addition of A's and addition of A's and G's and so on. Okay? So the calculator code remains the same. Okay, now that allows us to do some really groovy things. So we've done that. We have the two views. Now, before, we just poked a hole in Conway. Okay? So if we look here, we just poked a hole in Conway. But look, there's a container and there's a container. Now, do we have lying around somewhere a generalized notion of container? How about a monad? So we could actually make this thing not only parametric in A, but parametric in some notion of monad. So I don't know how you're collecting your stuff. You just tell me how you're collecting it. And then let's see if we can make the arithmetic work. Okay, well, it turns out that when we do that, oops. There we are. When we do that, it just works. And again, the proof is in the code, right? Code talks, and we know what else walks. So you can go look at the repo, and I'll make sure that you have the URL for this video. And you can see that the calculator for this thing, the calculator code, remains the same. Okay? That means, therefore, that we can build notions of quantity as rich as the field of the real numbers over arbitrary monads. So in other words, Conway's beautiful construction generalizes that far, which is, to me, that was really striking, right? And in fact, I guess what I want to say is that we've seen two generalizations. One is we poke a hole in Conway Games, and any first-year CS student, picking up Haskell for the first time, could have made this observation, right? That's a gift that computer science gives back to society. That by framing problems in this way, we see generalizations. We get to stand on the shoulders of a giant like Conway and see a new thing, right? But then once we've stood that far, we can stand that far again, which I think is absolutely beautiful. It's really something that computer science gives back to the scientific community at large. So let's take a step back. So it's like I'm always fond of that image. So I took it apart and rebuilt it, but what do I do with all these parts over here, right? So it turns out in Scala, set A inherits from the function from A to Boolean. And the consequence of that was absolutely and utterly surprising to me. It means that the variance constraints between list and set differ in Scala. So how did I discover this? Well, I was writing the code for this blog post, or this talk, and I had originally written the Conway Games in terms of list rather than set. But then I said, well, it's actually sets, it's duplicate free and order insensitive. Let me go and replace all the instances of lists with set. So I did that, and the compiler says, oh, I'm sorry, you can't do that. What? Why not? Oh, well, list and set have different variances. Really? That's not mathematically sound. That's not a good plan. So it's not consistent. I mean, you could say that set means something different than we think of in terms of set and list, right? It's like when I use a word, it means what I want it to mean kind of approach. So I actually had to write my own set for this talk. So you want to talk about, no reuse. Yeah. I didn't get to use the basic collections of set in this talk. So to me, that really brought home the content. So last 2 points, and then I'm out of here.
You make it sound like we're trying to rush you out. This is great.
Cool. So what I want to say, and referring back to James, whose comment I really appreciate, and it was inspiring to me, was that scaling the web is not about just volume or load or sheer numbers. Okay, scaling the web is as much about complexity. I could have the most scalable architecture on the planet, but if it's so complex that nobody can code to it, it's useless, right? So the crucial thing is finding abstractions that give us performance in terms of the sheer numbers, and also usability and understandability in terms of human appreciation, right? Because at the end of the day, humans are writing the code. Right, and that's what the Monadic API does, and that's what I was trying to suggest, which is that we see a pattern all the way back here. We see this pattern, which is the Conway game. We say, huh, that reminds me of something, right? And then first we generalize just by poking a hole in it. Oh, that reminds me of something, and we generalize yet again, and this game of generalization, it both scales performance-wise and scales complexity-wise, right? So that's the promise here, and then the last point is that I want to point back all the way to the Channel 9 talk that I did with Brian Beckman.
Okay, excellent.
Okay, because in that conversation we were talking about the relationship between monads and a notion of coordinate or location. Yep. So Conway's idea, Conway has a very strong and powerful intuition. He says a location is something I can point to from the left and the right. And this actually goes back to data kind cuts. Okay, and what we've shown is that we can actually give a presentation of that in terms of monads. Okay, so there's the notion of location directly in terms of monadic structure. So that gives a big check yes to Brian's intuition. Okay, Uwe's idea of the zipper is exactly the same kind of approach. What he says is, I'm going to do a different kind of splitting. Instead of splitting left and right along the same order, but pointing in opposite directions, I'm going to split in terms of context, like some position in a data structure and the rest of the data structure. But it's the same idea. It's a splitting, and the location is the thing in between. Right? And that also has, as we talked about last time with Brian, a monadic presentation. Now the promise and the beauty of this is by putting these two on the same footing, we can begin to compare and analyze them. Right? So to the best of my knowledge, that's never been done before. Right? So that's another beauty of the monadic design pattern. Well, that's all, kids.
Awesome, man.
Oh, thank you. This has been a great opportunity. Thank you, Charles. I really appreciate it.
Hey, man, thank you. We will see you again.
Oh, great.
Excellent. Cheers.
Cheers.
Great work, actually.